If you're driving and the oil light comes on, does that mean that you need to stop your car immediately because you have no oil? Or is it that you probably need to have a look at it at some point? The same applies to your saturation. If your saturation drops below 94, you don't know how quickly it's going to drop and you don't know how bad it's going to get. You just know that there's a problem. And in the same way that your dashboard has an oil light that comes on, you need to get it checked out. How's it guys, and welcome back to my channel. Today we're doing something super important. And if you use saturation probes or you read saturation readings, this is really important and a lot of people get this very wrong. It's called the oxygen dissociation curve. And what this is that it is a curve that's on a graph that has an X and a Y axis. The Y axis is the saturation of hemoglobin, the oxygen saturation of hemoglobin, and the Y axis is the SpO2, which is the partial pressure of oxygen. Partial pressure of carbon dioxide is explained in the best way of that all the gases in air are separated into their own pressures. And so there's oxygen, nitrogen, CO2, and all the other gases. Partial pressure of carbon dioxide, or PCO2, partial pressure of CO2, is just when you take out all the other gases, how much CO2 is there in that gas. Why is this important? Well, a lot of people read a saturation probe and go, well, 90% is pretty good. But they don't realize that the pass mark, in terms of what you think you're reading, is actually 94%. If you're any lower than 94%, you or the patient is not doing very well. And if you're any higher than 94%, you're probably in a good place. And that is why the oxygen dissociation curve is super important. So if we look at this shape here, this shape is called a sigmoid curve. And what that really means is that, as you can see at the top, it is quite flat. And as soon as you get past 93, 94%, it suddenly becomes a really steep curve, kind of like you're falling out of a plane. That's where the problem comes in, that the difference between 99 and 94 is a lot less than a difference between 94 and 90. And then obviously 90 to 85 is even greater. That is where the trouble comes. When you're looking at someone and the saturation is 92, it could be a whole lot worse than someone who's at 94, and it's hard to tell because the curve is so sharp. The other things to know about this curve is that it can actually shift to the left or to the right. If the graph shifts to the left, oxygen binds to hemoglobin much easier. So environments with low PCO2, so that's environments with low carbon dioxide, environments that have a higher pH, are more easier for oxygen to bind to hemoglobin, and that happens to be in your lungs, where there is less carbon dioxide and there is a higher pH. And the opposite is true. The shift will move to the right, where it is harder for oxygen to bind to hemoglobin, and actually makes it more likely that the oxygen leaves the hemoglobin and goes into the bloodstream. This is environments where there is a higher level of CO2 and a lower pH, like your fingers and toes and your body organs. So the body's been designed so that in your lungs, the graph shifts to the left, and in your fingers, the graph shifts to the right. But obviously, if the body is sick in entirety, if there's a systemic issue, if your body's pH is lower, the graph shifts to the right, which makes it harder for oxygen to bind to hemoglobin, which then makes it harder to oxygenate someone who has a higher pH. You understand where this complication comes in. So when you see a graph like this, is 1, 2, or 3 better or worse? And that's pretty much the sum of the sigmoid curve. The other thing that's really interesting about this curve is that if you invert the curve, it points directly to the subscribe button. And I bet you didn't know that. If you enjoyed this video, make sure you check out this one, because this will really help you better understand this topic.